Hey you all, sorry I couldn't be there today. So, really important and real quick, make sure that you got the new packet because you need the second page of these notes that I'm going to go over. You only have the first page. So, the last page of this thermochemistry section is the packet that should be passed out to you in class. I do think I remember to get these hole punched this time. If I didn't remember, there's a 3-hole punch at the front table in front of my desk. So to wrap up our thermochemistry unit, we are going to look at phase changes and heating curves. Last time we looked at enthalpy, and when we were looking at enthalpy, we did the summation equation and we were looking at the heat of formation. So when we were looking at the heat of formation, remember it looked like this delta H. It had this little, looks like a degree symbol, but we call that a knot. And then it had a subscript F with it, and that stood for heat of formation. So that's how much our enthalpy is required to change in order to form a compound from its elemental substances. Now, looking at heat of formation is helpful when we're looking at the formation of a compound, but there are other types of enthalpies and enthalpy changes that can be useful too. Specifically, we are going to look at some of these enthalpies that describe the amount of heat, and remember that's just thermal energy, that's required in order to, if we want to burn 1 mole of a substance, we call that the heat of combustion. If we want to take 1 mole of a liquid and turn it into a gas, so we're going from the liquid phase to the gas phase, we are going to call that our heat of vaporization. When I'm going from 1 mole of a solid to a liquid, I'm going to call that my heat of fusion. When I'm going from 1 mole of a gas to a liquid, which if you notice, these two are opposites of each other. So going from 1 mole of a gas to a liquid is my heat of condensation. And going from 1 mole of a liquid to a solid is my heat of solidification. So you may have heard these terms like vaporization or evaporate. You all have heard of solid to liquid as melting. So that's describing what's happening. Condensing, so when we have fog, or if you have a glass of water and the outside starts looking foggy because some of the water in the air is condensing onto the cold glass. And then liquid to a solid is probably what you have heard as freezing. So when we're talking about these enthalpies, I talk about them as the heat of some sort of change. So this is the physical change that's happening. So it's a physical description of the change, whereas these other terms, these are describing the enthalpies. So they're unique to the enthalpies. So based on this information, you should notice, and I pointed out one of them, that we have these processes that are opposites. So if we go from a liquid to a gas, that's the opposite of going from a gas to a liquid. So we've been talking about opposites a lot, and we've been talking about positives and negatives, but we've also been talking about endothermic and exothermic. So we're going to have these processes, and going one direction, it would be endothermic, and going the other direction, it would be exothermic. So the numerical value of that enthalpy change is not going to change, but the signs do. So remember, if delta H is greater than 0, that means we have absorbed energy, and that is my endothermic reaction. If delta H is less than 0, it's an exothermic reaction. If we think of particle motion and how much energy my particles have, my solid particles are packed tightly together and are just vibrating. When I move to the liquid phase, my particles will flow. And then when I move to the gas phase, they actually are moving rapidly in random motion and filling up their entire volume of their container. So as we move from solid to liquid to gas, my energy increases. Remember, heat is all about energy. It's the thermal energy that we have. So in this case, we're talking about thermal kinetic energy because my particles are moving. So if my energy is increasing, that means that I am absorbing energy. Which means that these states in this order, as I move in this direction, these are endothermic processes. So if I was to go backwards, if I was going from a gas to a liquid to a solid, my particles have less energy, so my energy decreases. That means I'm releasing energy. And these are exothermic. Okay, and then just as a reminder, these are molar enthalpies. So if you look, we had mole, 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 mole. So in today's work, if we're talking about a phase change where we go from one state of matter to another, you have to make sure that you are using a molar enthalpy. So the trick to figure out if it's a molar enthalpy is if you look at a table, it has moles in it. I am going to give you a table and you can look up the molar enthalpy that you need to figure out the enthalpy change, or you can calculate this depending on the information that you're given. So we're going to do example number 24 first. So for each of these, you just need to describe whether it is an endothermic process or an exothermic process. So what we have for A is a physical change because I have the same substance. I'm just going from a liquid to a gas. So my liquid particles have lower energy than my gaseous particles, which means that they have to gain energy in order to move to that gas state. So this is endothermic. The opposite is true. As I move from a liquid to a solid, I need to lose some of that energy so that my particles calm down, and instead of flowing, they just go into place and vibrate nicely next to each other. So this would be an exothermic reaction. In D, we go from a gas to a liquid, so that is another step down in an exothermic reaction. And when we go from the solid to a liquid, we need heat. Ice does not melt unless you add heat. So that is absorbing energy and endothermic reaction. For C, in this case, you have to look at the states of your reactants and the states of your products. Over on my reactant side, I have two gases. On my product side, I have gas, but I also have this liquid. So what that means is somewhere along the way, I lost some of that energy that I needed to maintain both of my gases. So that means energy was released, and this is also an exothermic reaction. So A, B, D, and E are describing physical changes, physical processes. and C is talking about a chemical change and a chemical process. Just a second ago, I mentioned that sometimes I can have you calculate a delta H value, one of these thermal enthalpies. So what we're looking at in number 25, it's asking what is the heat of vaporization of acetic acid if 0.700 moles requires, I want you to change that in your notes to, instead of produces, I want you to change that to requires 1,640 kilojoules of heat as it moves from a liquid to a gas. Now, if we look at this table, again, I mentioned these are always going to be given to you in kilojoules per mole. So if we look, we have kilojoules and we have moles. So to figure out my heat of vaporization, all I have to do is take the energy that it gives me in kilojoules and divide it by however many moles of my substance that I might have. So when I take 1,640 and I divide it by 0.7, I get this long number, but I want to make sure that I answer the right number of sig figs. Each of these numbers has 3, so I am going to round this answer to 3 sig figs, which would be 2,340. So that is the number part of my answer. Now, if we look, I didn't cancel out any of my units. So I have kilojoules per mole, which is how those enthalpy changes are recorded for my molar enthalpies. It's always going to be kilojoules per mole. Now, to figure out whether it's positive or negative, this one gave you a clue because it says that we're moving from a liquid to a gas, which means you know that it's endothermic and it has to be positive. Otherwise, just pay attention to the word. So if we hadn't changed this produces, we would have gotten our sign wrong because produces means released energy. So that would have been a negative 1,640, but that's just a typo on my part. So make sure you change that to requires, otherwise you're going to be confused why this is positive whenever the way it's written, you would think it would be negative. Moving on now to the last page of our thermochemistry packet in the chemistry workbook that we are creating, we're going to talk about heating curves. So in a heating curve, we are going to use a system of equations, and just like Hess's law is like a puzzle, heating curves are also like a puzzle, except in Hess's law, we have the pieces. In our heating curve, we have to make sure that we are building our pieces ourselves. So if we want to look at the overall change of a substance as it's going from one phase to another, we can do that step by step. So if we want to look at that overall change over time where we're going through multiple phase changes, we can use a heating curve. So whenever we have a phase change, there's 2 equations we're going to use, and both of these are on your equation sheet. I really encourage you to look at that equation sheet before your quiz on Friday to make sure you understand, first of all, where the equations from these sections are located on the equation sheet, what they actually look like, and how to look at the information on them and use the equations if you aren't understanding that already. So there's 2 possible equations. We're either going to use Q equals MC delta T, or we're going to use this equation Q equals N times delta H. I'll break those down for you in just a little bit. So we're going to use Q equals MC delta T during a temperature change. Okay, delta T, temperature change. So during a phase change, we're going to use Q equals N delta H because my temperature is not changing. It's just my enthalpy that's changing. You need to pay special attention because this delta H value is going to vary based on what specific phase change is occurring. So let's fill in some information on this heating curve. So this is a heating curve that someone has created of water. We know that it's the heating curve for water because I have a phase change at 0 degrees Celsius and I have a phase change at 100 degrees Celsius. So that's my melting point and my boiling point of water. So that's how I know that this is the heating curve of water. Now I mentioned over here on this side, my y-axis is going to be my temperature. Usually that'll be in degrees Celsius. That's what we've been using. That is what we will keep using. The bottom, my x-axis. This is usually referred to two different ways. The way that I want you to think about my x-axis is in terms of my energy. So I want you to think of this in terms of energy. Other ways that you might see my x-axis titled would be time, so the amount of time that progresses, or my heat. But remember, heat and energy, they're the same things. It's just heat is a specific kind of energy. So I want you to use energy, okay? So if we look at these blanks, and we have these two different processes. So as we move from A to B, we have ice, we have solid water. As we move from C to D, we have water, which is water in its liquid state. And as we move from E up, we have steam, which is water as a gas. So we have our three different states of matter represented. We also have then phase changes. So as we move from B to C, that's where I'm going from a solid to a liquid. So I have melting. And as I would move from D to E, that is where I would have vaporization. If I was going backwards, if I was doing a cooling curve instead, so let me do that in a different color. Let's do it in blue because it's a cooling curve. So if I was going backwards, the opposite of vaporization is condensation. And the opposite of melting is freezing. So for segments B, C, and D, E, these are my flat parts. These are my horizontal sections of my heating curve. When we have this horizontal section, that means my temperature is not changing. So I don't have a temperature change. So I can't use the Q equals MC delta T equation because delta T equals 0. And we know that since my line keeps moving, my energy is still continuing to increase. So for any horizontal section, my phase change sections, I need to use the equation Q equals N delta H. So delta H changes based on specific phase change. So am I melting? Am I condensing? What am I doing? Q, as always, stands for heat. And N, remember we talked about N stands for moles. Okay. So these other sections from A to B, from C to D, and from E up, where we have those diagonal sections. So that means that I am increasing both in temperature and in my energy. That's where we're going to use the equation Q equals MC delta T, the very first equation we started with in this section. So what we have here, it's just heating. We're just heating up. We're just heating our substance. Okay, and as a reminder, Q, again, that's heat. M is mass, so that's going to be in grams. C is my specific heat. And delta T is my temperature change, which remember is going to be my final minus my initial temperature. Okay. So I mentioned that these are kind of like puzzles, but we have to figure out the pieces and then put them together. So this is an example of what a heating curve problem is going to look like. It's going to ask you how much heat is absorbed by a substance, and it's going to tell you the temperature range that it experiences. So in number 26, we have 25.0 grams of water. It starts at 25 degrees Celsius and it ends at 110 degrees Celsius. So here's some information that the problem gives me. It tells me my molar mass of water. It tells me the point at which water boils, the temperature at which it boils and starts evaporating, going through a phase change. It tells me the specific heat of liquid water. That's what the L stands for. And it tells me the heat of vaporization of water. So I need you to write in the specific heat of water when it's a gas. Its specific heat in its gaseous state is 2.01 joules per gram degree Celsius. We're going to need all of these little bits and bobs and pieces, okay? So when I look at these problems, I write down how many steps I have, what equation I need to use for each step, and then I do the math for it. So we have to think about what's happening. We have liquid water because it's at 25 degrees Celsius, so I know that water is a liquid between 0 and 100. So my first piece, I know if water boils at 100 degrees Celsius and I'm going from 25 to 110 degrees, I'm going to have a phase change from my liquid to my gas state at 100. So that means I'm going to start with liquid water. It's going to go from 25 degrees to 100 degrees. Okay, then when it gets to 100 degrees, I'm going to go from a liquid to a gas. And then I'm going to have a gas at 100 degrees that is going to be heated until it reaches 110 degrees. So I have 1, 2, 3 different steps in this heating curve. I need to use 3 equations for this problem. So anytime where I'm just increasing my temperature, where I have a temperature change, I'm going to use the equation Q equals mc delta T. So I'll use that for both of these steps, 1 and 3. When I have a phase change, I have to use the equation N delta H. In this case, since we are going from a liquid to a gas, I need my heat of vaporization. So I needed to make sure to fill in the correct information. So let's substitute in our numbers. We have our mass, our specific heat. It's going to change because in 1 I have a liquid, in 3 I have a gas. So in my first equation, I need to use the specific heat of liquid water. And then my temperature change, my final temperature that I have a liquid is 100 degrees Celsius. Because at 100 degrees Celsius, those particles are going to start becoming gas particles. So I'm not going to have liquid particles anymore. Okay, so that's all the information for step 1. Step number 2, to find moles, remember we just take our mass divided by our molar mass. That equation is on your equation sheet also. So I take my mass in grams and divide it by my molar mass of water. And then I'm going to take this times that delta H value, which is 40.7 kilojoules per mole. And then for my last step, I still have the same mass of water. I haven't done anything to lose any mass or change any mass into anything else, but I have changed what state I'm in, so I need to make sure that I use the right specific heat. So since water is now a gas, I need to use the specific heat for water in its gas state. And its temperature change, the final temperature in my problem is 110 degrees. And the initial temperature of my gas isn't 25 degrees. I don't have gas until I have 100 degrees. So my initial temperature of my gas is my melting point, my boiling point. So this is everything that's filled in. Let's go through and let's cancel out our units real quick. So I have grams that will cancel in MC delta T equations. It's also going to cancel out here. All I would be left with is moles, since I would have moles left here and moles over there, that cancels out. Degrees Celsius can go away. So all I'm left with are kilojoules and joules. Those are units of energy or heat, and that's what I'm trying to find. So I've got these probably set up correctly. So let's go ahead and do the math on these problems. So when I type this first one into my calculator, I'm going to type in 25 times 4.184 times, now I need to start a set of parentheses. I'm going to take 100 minus 25. You could also just do that mental math. That one's pretty easy. It's 75. So when I close that parenthesis, it calculated for that. I have to make sure to hit the equal sign again. When I hit the equal sign again, this gives me my final answer, which is 7,845. We're going to leave all of that for now. When we're doing multiple step equations, leave any rounding for the very, very end. Now, that doesn't mean you have to write 9 decimal points in. Give yourself 3 or 4. You don't have to go too crazy, but you don't want to round anything yet. For my next equation, I'm just going to take 25 divided by 18. I take my mass divided by my molar mass, and then I'm going to multiply that by my heat of vaporization. So I get 56.528. Now remember, this one's in kilojoules. And then finally, my third equation, I'm going to take 25 times 2.01 times, it's going to be 10, but let's just do it the whole way so you can see these parentheses and practice on your own. And then for this one, we get 502.5 joules. Now, the last thing that we need to do, since we have 3 different processes, we're going to take our system of equations, and just like with Hess's law, we're going to add everything together. But I don't have all of my units the same. I need to have all of my units the same before I can add these together. Personally, I like putting things in kilojoules as long as I have really large numbers of joules. So I'm going to turn everything into kilojoules before I add it together, because I have to have the same units in order to add them equally together. Otherwise, I'm going to end up with some really weird thing. So the numbers that I'm going to add together are my kilojoules, and since a kilojoule is equal to 1,000 joules, I just have to take my joules and divide them by 3, or I can think of that as moving my decimal point 3 places to the left. So I'm going to take 7.845 plus 56.528 plus 502.5. And when we put that into my calculator, okay, let's double check to make sure I entered everything in correctly to save me from hitting it twice. So I'm going to get 566.873. That's what my calculator says my answer is, and those were all kilojoules, so that's my unit. Remember, everything needs a unit. But we're in chemistry class, so we need to care about our sig figs. So for these problems, even though we do addition and subtraction as our last step, these are still technically going to be rounded numbers. So I would like you to follow the multiplication and division rules, which means we're limited by our fewest number of sig figs. So we have 3, 3, and 2. The fewest number is 2. So I'm going to go to my second significant figure, look to the number to the right, and my final answer will be 570 kilojoules. And that would be my final answer. Technically, I found Q, but just make sure that you would have the 570 kilojoules. Now, these are worth a lot of points. So, you can get points for telling me what's happening. You can get points for identifying which equation that you would need to use at each section. You get points for finding each of these separate answers. You get a point for knowing you need to add it together, and then you'd have points for sig figs and units. So these heating curve problems can be confusing. You can get lost, but try and show me as much as you can remember. Remember the process, and you get a really big payout for these problems. So the other really important thing to know about heating curves is what happens at the different sections. So knowing if I have my diagonal segments of the graphs and that those are my heating sections, that's going to be really important, and you want to make sure that you understand that. And then at the other sections where we have our horizontal sections, and my horizontal sections represent my phase changes. That's also really important, and I would make sure I would know that going into your quiz on Friday. Your quiz on Friday is 15 points. It is mainly multiple choice. I think I put in 1 or 2 fill in the blank or provide an answer questions. So for the most part, you don't have to worry about sig figs, but they are always there. Always practice our sig figs. You'll be allowed to use a calculator, scratch paper, a periodic table, and an equation sheet. I will have your official test quiz copies available to you that we'll pass out and share. Hopefully I get to talk to you all today at the end of class, and I'm able to join the meet if my toddler cooperates. But if not, I will keep you all updated as to progress. Still plan on taking a quiz on Friday. If you need help, reach out to me. I will be available. So thank you for hanging on to this lecture. It is definitely way different than working in class together, but I appreciate your patience, and I hope that you were able to get your notes filled in. I don't have any papers to pass out to you today, but I have put some practice problems in Google Classroom as like an online assignment. So check that out. Start working on your reviews. Look over all of those answer keys. Make sure you understand how to get all of those answers. Hopefully you got the heat and calorimetry homework passed back to you if you got that turned into me earlier. I marked out anything that I wouldn't have given full credit for. So go back and redo those. Study, study, study. Quiz is Friday. We'll have review all day on Monday next week. And then Wednesday, September 1st, will be your exam. I am ready with answers when you come ready with questions. Have a good day. Hopefully I'll talk to you soon.